Welcome to the pre-recording of lecture 36 of MCS 572 on the GPU accelerated QR. So this is lecture 36 following 35 on parallel Gaussian elimination. So in a way this is a sequel, also more fitting in the applications side of the course. So in some applications, extra precision is needed, and the middle section on multiple double arithmetic is kind of making the motivation for using graphics processing units to compensate for the cost overhead of multiple double arithmetic. I will try to make this lecture as self-contained as possible, starting with the linear algebra routines to define projectors and reflectors. The householder QR, at least the blocked version, is very rich in matrix multiplication and therefore very well suited for GPU acceleration. So in this course we spent quite some time using the matrix multiplication as somehow a running example, as one of the major building blocks. The blocked householder QR is one of the algorithms that illustrates how the matrix multiplication is applied in the WY representation for the householder QR. So I will end with some experimental results for least squares solving, a very commonly occurring operation in various fields of science and engineering. Okay, so let us start with some very basic construction. So this comes from a numerical analysis class where orthogonality is one of the operations that will lead to accuracy. So if you have two vectors of the same norm, same length if you like, then their difference and their sum are perpendicular onto each other. And this can be very easily verified. So this works in any dimension, be it dimension 2, 3, or any. So it also settles the notation. So the T is the transpose. We are using the 2 norm here. Okay, so with that we can build, so the next ingredient is a projection operator. So we can make matrices from vectors. So if you have a vector, we typically write the vector as one column, so 3 rows, 1 column. Then the transpose is a row. If you multiply a column vector with a row vector, then you have a matrix. So Z times Z transpose is a matrix, a square matrix. On the other hand, if you place the transpose in between, then you are multiplying a row vector with a column vector and you obtain a number. So these are matrices that are also called idempotent. So if you apply them twice, so a matrix times a vector can be seen as a linear map, so as an operator that makes new vectors from other vectors. Well, if you do this twice, then you can see here at the last line that you obtain the original matrix. So that's one of the properties of projection operators. Okay, how are we going to use this projection operator? Well, in this definition here, we have the lemma. Remember how we construct orthogonal vectors from vectors that are of equal length. We have the projection operator. And with that, the vector z is now defined as the difference of two vectors. And with that, you can define a householder reflector. So the I is the identity matrix. The matrix H is an orthogonal matrix. Orthogonal matrices are very fun to work with. The inverse of the orthogonal matrix is the transpose. So you can see the property of orthogonality here verified using the property again that the projection operator with itself multiplied with itself is itself again. So householder reflectors, they are big matrices, square matrices, but they allow actually for a very compact definition. So you only need to know the vector z. So there are symmetric orthogonal matrices. Okay, so far so good. So far this has all been quite interesting. But what do you actually really want to do with this? Here is the algebraic derivation of the reflector property. If you have two non-zero vectors, then you can turn one vector into the other by this multiplication with the matrix H. So this is verified. So this is the two the recipe. The two first lines define the vector z based on x and y, and also define the matrix H. And what is remaining then, so the 6 equalities on the slide verify step by step the reflector property. So if we work out the algebra and rearrange, then we use in the last step the orthogonality of the vector z. So the vector z is the difference of the two vectors. So this is the lemma that is applied here. We have that everything collapses to the vector y. Okay, it's too much algebra, perhaps, so time for a picture. And in some sense, this picture illustrates the essence, what we are going to do. The vector x can be any vector. So here, for simplicity, this is a two-dimensional vector in the plane. Otherwise, it would be difficult it's harder to draw in 3 dimensions. But you see the y vector is a vector that is horizontal. It will be the vector that is parallel with the 1, 0 vector. Remember what we did in the previous lecture with row reduction. We are simplifying the matrix to an upper triangular matrix. And that's actually also the R in the QR. The lecture here is kind of suspenseful, but you see with this picture what we are trying to do. We're going to try to introduce zeros, making any given matrix, making it upper triangular. And the neat thing is, so it's not obvious, it's not at all clear because we work in the plane, but this construction works in complete generality. In one matrix vector multiplication, we can introduce as many zeros as there are below the diagonal. And I should say that the property, the picture here, makes this reflection kind of, should make this reflection around the bisector also possible. So the algorithms that we consider have a geometric interpretation. Each time we normalize the vector that we want to reduce to a vector parallel to a unit vector. We therefore also compute the vector y. So the first component will be the norm of x, and we therefore introduce many zeros all at once. The orthogonality will lead to very accurate computations. So that's actually also the main message that we also always say in numerical analysis. Okay, here an example, still algebraically, but if you understand it for a 3 by 2 matrix, so we have fat A1 is a column vector, fat A2 is also a 3 by 1 vector. So we introduce zeros under the diagonal in the first column by computing the norm. And then we, so that will be our first householder reflector. The second column is then defined by making the second householder reflector using the components of the product of the first householder matrix with the second vector. So you see that it looks like a lot of work in the sense that we are going to have a whole sequence of reflector matrices, but the dimension is actually shrinking in each step. So what we are doing is that we are using the householder matrices to build an upper triangular matrix called R, and the orthogonal matrix, so the QR, then arises from the multiplication by the householder matrices. So if we accumulate the householder matrices, and by the way, the accumulation of the householder matrices is actually those vectors z that we were called at the last time. So we can explicitly compute these matrices, but it will turn out that we will have a very efficient representation of these reflectors. Okay, so this is DQR factorization. In other courses, you may see the Gram-Schmidt orthogonalization, which has a more clearly defined, which also have a very nice geometric representation that is sometimes seen as an alternative. QR, this householder QR is twice as efficient as the Gram-Schmidt. Here you see the evolution of the algorithm, the evolution of the matrix. So how in a 4 by 4 matrix we gradually introduce more and more zeros. Okay, now comes the code. So there are two steps in the two functions that will define the householder QR. Here is the first householder function, the householder vector. So the reflection operators, they are defined by a vector and a beta constant. Here is the code for defining both the vector v. So you see that we take a vector x, we select the y. The y is everything that is below. We compute the inner product. The vector x is therefore already normalized. So the first component of v is 1. The y is copied, and we define the beta. So it could be that the beta is 0, but that means that then the vector is essentially already consists of all zeros below the diagonal. So there's nothing to do when the beta is 0. And then we define the beta via the norm, the first norm of x1, and the norm of everything, the sigma, which is actually the norm of everything below. Okay, that's actually the hardest part. Then here you see the householder QR defined in a high-level matrix vector notation with the proper subselection of the matrices. So we will return an orthogonal matrix, the Q, and the upper triangular matrix R. And you see here the call to the definition of V and the beta called B here, and the update of the upper triangular matrix and the orthogonal matrix. So this is pseudocode, but at the same time also executable. So this is a valid Julia code that you can run. So I will post on the website the Jupyter notebook that has the steps to update R and Q more explicitly. So if you look into the code, then you see that the matrix V times V transpose occurs twice. So this would be extremely inefficient to actually run, although for small examples it really doesn't matter. But for efficient implementations, this would probably not do if the V times V transpose is explicitly computed as a matrix. All right. Now comes more the efficient WY representation. So we are using here a description that is in place. So we can accumulate the householder reflectors in a separate matrix, and the original matrix is overwritten by the upper triangular part. So this is the blocked householder QR. So in the previous lecture on parallel Gaussian elimination, we presented a tiled version and emphasizing there the left-looking data movements. So in a way, also the same arguments apply actually also here. So what are the main references? So there is the WY representation that I will define in the next slide. So this was defined in 87, and my edition of the classic matrix computation dates from 96. So these are the two main references for the first part of this lecture. Here the evolution of the matrices. So we update the matrices. So we have the I matrix, so the identity matrix, that is gradually replaced with the definition of the orthogonal matrix, the reflector matrices. And you can also see how the matrix A gets overwritten by the upper triangular parts of the matrix. So this is an evolution of the blocked matrix. Then here is the summary of the blocked householder QR. The householder matrices are represented in a WY format. So this is the aggregation as it is defined in the 1987 paper. So we are computing the Y and the W matrices. So the Y will store the householder vector. The W's will the W matrix is defined by the householder vectors with the betas. Then if you have the W's and the Y's, then with that representation, the updates to Q and R are defined via matrix vector products. So one could already have discovered, so the algorithm in the house QR already updated Q and R in 2 lines. So here you see the lines again. So there are the matrix multiplications that will make it really suitable for GPU acceleration. So in a way, as the application part of this course, again, as we spent so much time on GPU acceleration with matrix products, you can see that this is really beneficial now. Okay, so this is the first part of the lecture, the first 20 minutes. In some sense, this is a little bit of fused course. A linear algebra course would now continue. I haven't really justified the WY representation. I leave this as an exercise. It's also not really a numerical analysis course. I just stated that it is more numerically stable. A numerical analysis course would also examine that in greater detail, also with respect to the conditioning. So one of the great virtues of the QR representation is that it is also numerically stable on ill-conditioned matrices. So that means that it's also one of the components in rank revealing algorithms. Okay, so let's now switch gears a little bit. So we have introduced multiple double arithmetic. Multiple double arithmetic extends the floating point arithmetic, extends the accuracy, the range of numbers that can be represented accurately with still using the hardware 64-bit arithmetic. So here is an example of one of the great properties of multiple double arithmetic. So if you are computing the number 8, and 8 can be exactly represented by 64-bit precision, you actually don't need that much. But you see then that the second double is actually the precision at which you have or actually the accuracy, is the accuracy which here corresponds to the working precision. So normally you have about 16 decimal places when you work with 64-bit arithmetic. With double precision, this doubled to 32 decimal places. It doubles then again to about 64 decimal places with quad-double, and then it doubles again if you use octodouble. So also these algorithms are often applied in that sequence. So the nice thing is that you have a predictable overhead. The overhead is non-negligible, although double correspond to complex double. And often the problems become compute bound, so that actually the extra cost overhead is actually absorbed. So sometimes you get with double arithmetic twice the accuracy with about twice the amount of work. This is kind of very interesting. So, but one of the virtues of this course is that you can understand why this is possible. Downsides of this, so you are still limited if you want to work with, say, 17 decimal places. You can't do this, so you have fixed multiples. It's not really true multi-precision then in the actual sense of the word. You can't really say I want to compute with 17 bits. The exponent is also fixed, so you can still have an overflow and an underflow when your numbers start to grow or start to decrease. My motivation to work for this, and often I get in my earlier papers I got this comment a lot, why actually are you doing this? Because people in numerical analysis, they have the game that if you want, say, if you're happy with 8 decimal places, then you try to compute with 8 decimal places. So that's why there is the mixed precision trend that is in some sense also part of this computations here. Okay, I'm using Newton's method a lot to compute power series. If you have a very nice power series like the exponential, and exponentials are quite nice if you start to multiply them. The binomial theorem. There is the exponential growth of the coefficients. Well, with the exponentials, you actually don't really have this. So exponentials are nice and for other reasons as well. But if you want many terms, and actually if you use a GPU, there's actually not really a reason to hold yourselves back with, say, 64. But then you see that the smallest number, the 1 over k factorial, is already 10 to the power minus 88. So if you want, actually, that's way below the precision actually of quad doubles. So here is kind of a motivational table that if you want to represent all the coefficients accurately in a power series for the exponential, then actually you should almost, if you are computing that, you should actually use that precision. There is the need hexadoubles, so I'm using Pascal and Volta computers, GPU cards. For hexadoubles, there is quite a huge overhead. I have already experiences with it, but you would actually need a little bit stronger graphics card. The punchline will also be that if your card supports teraflop performance, then you can compensate for quad double. Okay, here are the software packages, which are a lot of thanks to. There is the QD library, then there is the GQD library. So you see there's kind of about 10 years apart. And also observe that this is in a workshop on data management on new hardware. There is the most recent package that consists mainly of code generators, Campari, aimed for CUDA, which is the most recent version that I have been using to extend the quad double and double double arithmetic to octo double and also hexadouble. All right. All good and well, but here is the downside. So you can see there is the predictable overhead. To do one addition in double-double arithmetic, you need 20 additions. You need 20 64-bit floating point operations. For a multiplication, you need 32 64-bit floating point operation, and division is 70 64-bit floating point operations. So the average is 37 if you assume an equal likelihood of the operations. Quad double is 400. So here you have a back of the envelope operation. So you are working with a 2 some gigahertz sequential processor, and then you have 400, so it's about close to 900 or round off to 1000. So that gives you actually a terahertz that you would be needing, or that's how I justify the teraflop performance. So here are the GPUs that I've been using. So you can see the evolution of the core count, but also actually the thing that I would like to point out is that the frequency of one core of Volta is actually approaching the 2 gigahertz already. So the last GPU is in a gaming laptop. which also is very useful to use. So I mentioned comparison with the CPU. So using two different graphics cards is very convenient. Then you do not need to have the unfair comparison with one core on one CPU, which is kind of unrealistic. So instead, you compare two generations of two subsequent generations of GPUs. So here you have the peak performances. We would expect our code on Volta to run about 1.68 times faster if everything works well. So this is another way of examining the scalability. All right. I mentioned the Campari software. Campari will generate on data structures that are arrays, sequences of floats. So a multiple double, also a multiple 32-bit float, is represented by one array. Very convenient at first, but I know from experience that this is not very good for efficient memory coalescing, as we have considered earlier on in this course already. So one could still get away with double 2 and double 4, which are built-in types with a very good alignment in the software development kit of CUDA, the Compute Unified Device Architecture. But you get into trouble with complex quad double and also with octo double. The QD library was in this sense still very useful for giving somehow examples on how to implement a cosine, a sine, and a square root in multiple double precision. Okay, so I mentioned the number 8 that we computed. So 8 was one of my running examples when I developed when I gained computational experience with the Campari library. So you take a vector of random complex numbers, all on the unit circle, and then there is a property that says that this nice vector, so if you take 64 elements, then the norm, the 2 norm, will be 8. So, and this is a very nice test because you take random complex numbers. Okay, this is a summary. So in the course, we have mentioned the prefix sum algorithm that is being used as well. We have combined this so you can run this for very large vectors. For then actually you have several runs, several launches of kernels. There is a fine tuning that you want to do. So in some sense, I mentioned code generators. What you actually would like to do is that there will be an automated algorithm that generates the codes for any precision, for any size. We are not there yet, so one needs to be careful as your size of the numbers is growing. You have only limited fixed shared memory needs, so actually you have to adjust, fine-tune the sizes of the subsums that you can use. There is the performance cliff that you may run into, so it's sometimes very tempting to use anything in registers, certainly for double-double, perhaps also for quad-double, but if you're going to do complex octo-double, you have already significantly introduced the number of amplified the number of registers that you're going to use. So there are trade-offs to be made. Okay, so let's now go into the last part for the last 10 to 15 minutes. So in some sense, everything has already been said. So the key point is that The blocked householder QR involves many matrix products. So here is actually the heart of the algorithm. That will be where the intensities are happening, the updates of the Q, the updates of the R. Although it's not a bottleneck, I will indicate what the bottleneck is. I'm motivated by the multiple double arithmetic for power series, where the QR is essential as computing the accurately the leading terms of the power series. So that should have been indicated. I should have been stated that earlier. So there are GPU implementations. So in this course, this is probably already now the fourth time that the Volkov and Demel paper is mentioned. I got a lot out of the second reference, the paper by Kerr, Campbell, and Richards, which is very self-contained and very useful. So that was my key reference when I did the multiple double implementation. But there's also the technical report by Baboulin, Dongara, and Tomov. All right. So here is the definition of the parameters in the blocked accelerated householder QR. We are looking at a matrix that is tiled. So the matrix is m by n times m. So there is a little n, which is the size of a tile. The capital N is the number of tiles. Then we have the total number of rows, which should be larger than n times big N times little n. The output is an orthogonal m by m matrix. And then we also have the matrix A that gets overwritten by the upper triangular matrix R. So here are the main steps. So the algorithm runs over the number of tiles. So each time we compute the householder vectors, we do the reduction of one tile. We then arrive at what will become the bottleneck, the computation of W. So the Y is simply defined by the outcome of the first step. It will turn out that the W will be the bottleneck on all the GPUs that I have tried, and also this corresponds with what is reported in the literature. Nevertheless, the great gain in the algorithm is in steps 3 and 4. So this is where a lot of computations are happening. And this is where the true massive parallelism of a GPU is really coming into play. So you can really see that the teraflop performance pays off. So at some point, the bottom line here is that it is possible to reduce the cost of the total cost is actually still cubic in the dimension, but you can actually reduce this by a factor m. So there is a sweet spot of the dimensions, and this kind of happens when you realize teraflop performance, where you live in a world where there is a quadratic time algorithm for computing a QR implementation. So the implementation that I developed is written for multiple double precision. So this algorithm is not going to perform very well on 64-bit. So the 64-bit is only the reference. In some sense, that's often the first step what we do in a quadratically converging algorithm. We defined several times the compute to global memory access ratios. So they're actually extremely favorable for multiple double precision. So this is also here the main benefit. You go from double to double-double. You double the amount of data, But actually, the number of operations, remember the tables I've shown, the number of operations is 20 floating point operations for the addition. So your compute to global memory access is already 10 times higher compared to double arithmetic. So that's why these algorithms are actually so interesting if you are still somewhere at the beginner stage, if you don't do this all every day for a living. Okay, data staging is again important. I mentioned this earlier. So, a data staging algorithm is an algorithm that organizes the data for favorable memory movements from the global memory into shared memory into registers. So, in order for that to happen, adjacent threads must access adjacent memory locations, and you get that by storing your multiple doubles not as you would naturally think as numbers in a matrix. So instead of having, if you work with quad doubles, instead of having a matrix of quad doubles, you will have 4 matrices with the doubles sorted in order of significance. This seems cumbersome at first, but multiple double arithmetic is happening in staggered way. So you add matrices as you increase your precision. You also drop matrices and vectors as you go back to the original precisions. So the last 2 lines are referring to bank conflicts, a topic that we have covered earlier. Also the topic of efficient memory coalescing. All right, so in the remaining 5 minutes, I will discuss the experimental results. So there was the earlier lecture on solving triangular matrices. So generating a random triangular matrix in quadratic time is still something that I would like to know. So if you know an algorithm that does this efficiently, I had to generate my random triangular matrices via a QR because of that result that random triangular matrices are actually ill-conditioned. So what is important in the experimentations is that you are deciding on the number of threads in each block and also the number of blocks that you are going to use. So the minimum block size will be 32 because of the warp size, but sometimes it might be more. Also keep in mind that the Volta has 80 streaming multiprocessors. So actually it would be very good if you could work with 80 blocks. So that already gives an indication of the dimensions of matrices that we need to work with in order to keep the cards like Volta fully occupied. All right, I worked with 5 different GPUs, and the first so there are the Linux workstations. So the first one is already more than 10 years old. The V1, the Volta 100, comes from 2017. I purchased it in 2019. So these are not the most recent cards, but what you see, what I told earlier, the bottleneck, the computation of W. And you can see that the bottleneck becomes actually more bottleneck-like with the more recent cards. So with the first card, the computation of the W is still dwarfed with the other computations. So it's not the key kernel here, but you can see on the Volta, I did not optimize any further, but there you see that in the entire computation, so the computation of all kernels, half of all kernels was spent on the computation of the W. And this was in double precision. So on matrices of size 1024. So we have the 8 times 128. 8 blocks, 128 threads per block. That turned out to be kind of the most favorable. So there are the kernel flops, so you can time the time spent by all kernels, and then you can also compute the wall clock time. The flops are computed by counting, literally the float, I mean, not counting by hand, but for every kernel, there is a separate function that is going to compute the number of floating point operations using the tables, the overhead, the cost overhead tables for the multiple double arithmetic. So you see that this is also a compute bound problem. So there are memory transfers, but the kernel flops and the wall clock flops, they are bold, so more than 1 teraflop, 2.2 teraflops on Volta and 1.8 teraflops on Volta. So Pascal also realizes teraflop performance. The parameters 8 by 128 may not be most favorable for Kepler. So it seems like the RTX 2080 in the gaming laptop is outperforming Kepler, which is probably not entirely good in favor of Kepler, because Kepler, I think 192 might be a better parameter there for the number of threads in a block. So there is some uniformity here. So you can also see that the additions go very fast. I separated the additions from the multiplications. So counting the number of flops, the most computations are done in the matrix vector multiplications. Here written with the accumulation form. All right, so let's look at some bar graphs. I only have 2 minutes left. So you see here, if we are doubling the precision, then on the Volta, so we double the precisions, we double the dimensions, and you can see that if you do that, then actually the distinction between double and quad double is not that large anymore. So on matrices of dimension 2048, so we have a performance drop there with double precision. But you see that the bars, so there's a, so each unit up in the bar is a doubling in the time. So one has the theoretical bounds, so you have the cubic time. So if you double the dimension going from 512 to 1024, you would expect a multiplication by 8. But that is actually not happening. What is happening is that your GPU starts to get more and more occupied. So the GPU absorbs a lot of this increased theoretical factor. Then also there are the theoretical multipliers. So in going from double to quad double, you would expect an 11-fold increase in time. And then again, you would expect a 5-fold increase from quad double to octo double. But that is actually not at all observed. Again, because the problems become more compute bound and your GPU is capable of absorbing. There is then also the comparison between different GPUs. I would again say that there is the predictability. So on each, and essentially the scalability of the problems. So as you scale things up, so you are going, now I'm rescaling the precisions. then actually it's quite predictable per GPU. Observe the height of the bars. I mentioned the theoretical peak performance of Volta versus Pascal, and you can see that the red bar and the middle bar, the heights are actually quite relative with respect to each other. So that is the indication for the good scalability. We have seen roof line plots. So when I was talking about triangular system solving, this plot somehow did not make it in the lectures. So going towards applications, well, the QR, what do you do with the QR? Mainly you want to solve a linear system in the least square sense. So you have to do a back substitution. And for that, your dimensions need to be a lot higher. So you can see that you need to go to 80 times 256 to achieve teraflop performance. But still, so we have the green line in the plot and then the roof line. At the left of the green line, you have memory bound problems. So that actually goes up. With the at the right of the green line, you have compute bound. So all our dots computed with the arithmetic intensity, the dots actually are at the right of the green vertical line. And what happens is that at 32, so the isolated left dot there, then actually you are only occupying less than half of the GPU. All of a sudden, if you double the threads, you are occupying the GPU more and more, and your kernel time flops actually improves a lot. The arithmetic intensity is also improving a lot. Okay, so this is a summary slide. Just in saying that for the total least square solving, you shouldn't really that worried about the back substitution not being that performant, because if you look to a 1000 by 1000, the QR factorization essentially dominates the entire time. So, and you still achieve, you see actually on Volta, the total kernel time flops, and actually if you round up, the total wall clock time flops is actually 4 teraflops in octal double precision. The first column is corresponding the warning that I indicated. So for double precision, my code is not geared towards that. So the performance is probably there disappointing. One can also say that in double precision, 1000 by 1000 matrix is actually too small for the GPU. All right. I'm going over time. Here are some additional references. I mentioned I actually did not mention that much of the algorithms development. So the double-double arithmetic goes back to the float-float precision from the late 60s, early 70s. This is a course that follows numerical analysis, but computational geometry is also where the need is there for accurate, robust computation. So that's another source for double-double and multiple-double arithmetic. And then, of course, there is Julia. I used Julia. So there is the package multifloats that is going to outperform by great factors the big float. Of course, big float is true multi-precision, not entirely fair comparison. And then there is the MPLA pack. So I worked on my own self-contained version, but there is the MPLA pack that supports arbitrary multi-precision linear system solvers and also quad doubles. So that's also an additional references that needs to be consulted. Okay, the main takeaway from this is that blocked householder QR is a great application for matrix multiplication, well suited for GPU acceleration. You get teraflop performance already for low precision, for low dimensions when you work in multiple double precision. Here are 3 recommended exercises. So in a way, the purpose of this course is that you find your way into the literature. It's also an invitation for your own experimentation. So the course was this lecture started with a linear algebra introduction, but then kind of got cut short. If you are a mathematician, you may have been wondering why these formulas are the way they are. So that's actually certainly look at the literature, look at the paper of Bischoff and von Loon, the 1987 paper, look at matrix computations. Julia code was given for the householder QR. Well, build your own multiple double version. So there is high level performance, high performance in Julia. And another way to work would be to prototype, or actually in Julia you have immediate access to the BLAS routines. So you can actually also develop a fine-grained, a very detailed, even high-level multi-core QR by using the ideas we considered in the previous lecture, talking about the parallel Gaussian elimination and the tiled algorithms there. Okay, I ran 5 minutes over time, more than 5 minutes than what was budgeted. I hope it was worth it.